Good morning, students.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. Everyone, please put your attendance in this chat box. Don't forget. Okay, because I will take this one for extracting your attendance on day-to-day basis. So if you are not putting your attendance in this chat box, but you are still present in the class, then it will be very difficult. I will mark you absent, and then you can say that you were present, and I have to verify the proofs. Okay, so please don't do. You put your attendance on regular basis. I'll be now still okay 40. That means nearly all of you have joined. So I think I can start the discussion. I've also shared the textbook in the same sharing folder. I will I may add something, I may delete something as required. So you please always have the link for this lecture material components. Okay. Now yesterday I will follow some notes, and otherwise I may go beyond our discussion. So that's why we are maintaining this. So last class I talked about growth, right? Yes, microbial growth I was talking. So I'll just have the same discussion continue for a few more minutes. We'll also talk about fermentation requirement. I already talked. And you please follow the text what I am talking, okay? Otherwise, it will be very difficult for you to trace what discussion is going on, from what component you are discussing. So please have a look what is the study material, or maybe the text I am following. Maybe the discussion will be independent, but you please still carry on collecting those material as well. Okay, so in our last class, we talked about microbial growth. And if you remember correctly, I talked about the different phases of growth. I hope you remember microbial growth phases, right? Initially, nothing is growing, then so much growing, then slow down, and then falling. And those phases are known as lag. I talked about. This is logarithmic growth or log phase. This is fixed, stationary. There is no changing. And this is decline or death phase, right? Falling down. So basically, these are the things of any microbial growth standard. Every time, all microorganisms might not have lag phase. Okay, it is not necessary that everywhere lag phase will be there. If your microorganism is already growing in a media, and you are allowing it to grow in the same media, then there will be no lag phase, right? Every day you are coming to campus, you are already known how to deal, how to come inside, all those things you know. First time when you are coming, then you have to ask someone how to go to this department, like that. So similarly, if the microorganism is already growing in a given media, maybe for example, nutrient broth, you are already growing, then you are taking some microorganism and growing into another one. This time there should be no lag phase, because microorganism is already acclimatized to the same media, same temperature, so it already knows. So lag phase is not everywhere, you cannot see that. Okay, log phase is most productive phase most of the time. It is the more important phase, because this time biomass amount increases, logarithmic expansion it will happen, right? So 2 cell to 4 cell, 4 cell to 8 cell, 8 to 16 cell, like that, increasing. And last class I already talked about, okay, we are going to use a term that is known as specific growth rate. If you remember, that is, I told it is 1 by x dx dt. What is x? X is biomass concentration. X is cell concentration. Unit is gram per liter. Traditionally, we normally use the term gram per liter for our discussion. So, as I know already biomass concentration, and this is called specific growth rate. Please, now I will tell you one thing very important. For example, I know the microorganism. Okay, so for example, I'm talking microorganism is Escherichia coli. So for example, I'm talking microorganism is E. coli. For example, your media. For example, I'm using nutrient broth. Anyway, the composition of nutrient broth, all those things you will come to know from microbiology theory and lab. So basically, you will have peptone, yeast extract or beef extract, agar. If you are making a solid media, sodium chloride, so basic components are there. It is a complex media. Anyway, forget about that. So for example, I'm telling I'm having a microorganism E. coli. I'm growing on a nutrient broth. And for example, I'm also telling that temperature. For example, I'm growing at 35 degree. If the three things I am telling, so they have a growth rate, maximum specific growth rate, that is always fixed. The growth rate is mu max. I'll talk about mu max also. Maximum specific growth rate, that is always fixed. So I can say like this is your identity of the microorganism. It will not change if I take microorganism, if I talk temperature, if I say I'm using the media. So if you fix three things, then its specific maximum specific growth rate is always fixed. Now, okay, I talked about specific growth rate. How can I do that? How can I identify? So you remember one small calculation I will do today, and you please be careful. It will be always useful, not in this bioprocess class alone. Mu is known as specific growth rate. Now, one question will come. And you know how to do that, right? For example, let me talk about, I am starting a culture. Listen carefully. These classes little bit slow I will be going because involve of mathematics. So for example, there is a 35 cell. I am starting 35 cell I have inoculated. After 1 hour, for example, I will ask you questions. Be careful. I am having, for example, 42 cell. Just for example, 42 cell is happening after 1 hour. Another after 1 hour, for example, my cells, I mean to say microbial cell increases to 45 cell after another 1 hour. Of course, it is slowing down, right? It is not so fast. And you started because you have some media, right? If you listen and you can ask me, you can stop me. For example, I am growing this media in 100 gram per liter of glucose food, right? Media. Listen carefully. So I am starting with 35 cell. Concentration of media is 100 gram per liter. Then it is becoming, after 1 hour, it is becoming 42 cell. Then after another 1 hour, it is becoming 45 cell. Do you think glucose will remain same or it will decrease?
It will decrease.
Decrease, sir.
Yes, because it is a food, right? Food they are consuming. So for example, food is decreased to 89 gram per liter after 1 hour. For example, here it is 80 gram per liter, like that. I'm just drawing this picture. Same procedure I am also doing. Same procedure I'm also doing, but this time my glucose concentration is, for example, 50 gram per liter. I took little bit less concentration, but I'm taking same 35 microorganism. Starting microorganism amount is same. Do you think how many cells will be there? Do you think it will be 42 here? No, maybe something different. For example, this time I'm getting only 40 cells. Because why? Because my amount of food is little low here, right? Food is not so high. Here also after another 1 hour, maybe I'll get just 42. I'm just taking example only, okay? And 50 become 47, then become 45. This is food. Okay, this is glucose. Now, okay, these two pictures I drawn. I will ask you first question. What is the specific growth rate mu here? What is the mu here? I told you it is 1 by x dx dt. You should be able to tell me what is the mu in this phase. Can you tell me? So 35 become 42, yes, in 1 hour. So, and what is the starting? 35. So what I will do, 1 by 35. What is the change? Dx. change is 7, right? 35 is becoming 42. And time is 1 hour. So it is becoming 7 by 35. So 0.2, you can do that. So specific growth rate is becoming 0.2. What about the next hour? You see, here 42 is becoming 45. So this phase, what is the specific growth rate? 1 by 42. I'm taking example. Change is only 3. 42 is becoming 45. 3 change. Time is 1 hour. So it is becoming 3 by 42. So 1 by 14. So it is becoming 0.1 by 14, right? 1 by 14 means, for example, 0.07 approximately. So it is becoming 0.07 mu. So do you think mu is constant? No. You see, initially my mu is high, then mu is also changing. So specific growth rate is not constant. It also changes. No, it is not a constant. Now, in this case, I am starting with low concentration, and my growth rate will be definitely different. It will become 5 by 35. You can do that. Change is 5 divided by 35. So 1 by 7. So 0.1 something. 14. So in this case, my mu is 0.14. So what happens? Why this mu is changing? The reason is there. Here my substrate is different. Here also substrate is different. When substrate is consumed, here also substrate is different. So what is happening? Mu is not a constant, but it also depends on how much substrate I am having, food. Okay, so mu is not constant. Mu also change with time. You see, it is changing with time for a batch, and it changes across batch if my starting concentration of glucose or food is different. So essentially, I'll say that mu is also a function of substrate. For example, I'm writing S as the food substrate concentration. Okay, and from this concept, we have different kinds of model. One model you will probably using is monode model later on. So mu is actually depends on substrate concentration, initial mu. So mu max into S divided by S plus S. S is substrate concentration. Mu max is maximum specific growth rate. Maximum specific growth rate. And mu is specific growth rate. Then what is this? Why we are doing like this? So thing is that if we do in our last example, I told na, initial just 1 hour, but my glucose is 100. Here 1 hour, my glucose is 50. You see, when I'm having 50 gram at the very initial phase, specific growth rate is 0.14. When I'm doing 100 gram, specific growth rate initially is 0.2. So if I am doing multiple sets of batch study, I am not doing only one set, I am doing multiple sets. Okay, I took multiple flask. Are you understanding? I took multiple flask. Initial microorganism, whatever I am adding same, but glucose concentration is different. For example, here 10 gram per liter, here 20 gram per liter, here 50 gram per liter, here 100 gram per liter initially, starting. Of course, it will consume. And I am just measuring the very initial, starting 1 hour I am measuring. Not every time, long time I am not doing. Just 1 hour I will measure. And I will calculate their mu, separate mu. Are you getting the point? I am having 6 set of flask. Their glucose concentration is different. And I am adding microorganism also everywhere, no issue. Just immediately after 1 hour, I am measuring and I am calculating their mu. How to calculate mu? Already know, right? This is the formula for each of the case. Each case you will calculate mu. So if I am having substrate and if I am having a mu, if I draw this data, for example, first batch, second batch, third batch, fourth batch, fifth batch, sixth batch. If you do this, then you will see that you are getting a graph like this. That means After some glucose concentration, it will be saturated. It is no more increasing. Growth rate is no more increasing. Up to that only it will increase. If you increase substrate also, nothing is going to happen. So this specific growth rate is called mu max. I told you one equation, right? So at any time, mu is mu max into S divided by Ks plus S. Why? You can see the equation. If I say my substrate concentration is very, very high, that means what will happen? This divided by Ks plus S. So essentially, this is so big that I can ignore this, very small. Then S and S will cancel out, mu will become mu max. So when S is very high, mu is mu max. You see, this is mu max when S is very high. But when S is low, when S is very small, then what is the equation? Are you understanding? If you don't understand, you stop me. This is the equation we are using. Why? For example, S is very small. If S is very small, for example, S is 0.01, just for example, and Ks is 500, for example. Now, what is this? Ks plus S, right? So, Ks is bigger and S is very small. So, if I add very small with the very big one, do you think anything will change? It will be nearly 500 only. 500.01. It is very close to 500 itself. So, this addition is ignored. I can simply cancel. Okay, I am not adding any S. It is same thing. So, what will happen? Ks is constant. Mu max is also constant. So, what is happening? Mu is becoming proportional to substrate. You see this portion. This portion, what is happening? Linear, right? Like a straight line kind of things, it is increasing. S is increasing, mu is also increasing. So very fast phase, it is linearly increased. And when substrate is very high, then it will become saturated. That is called mu max. I hope, are you clear about what we are talking about?
Yes, sir.
All of you understood? How we are doing, how we should get the mu max, how we are studying this, you see? I am doing experiment only, and then I am trying to plot them. And it will become like this. So maximum specific growth rate, you can only find out like that way. That is known as maximum specific growth rate. Please keep in mind, I was talking like here. I was telling, na, if I know the microorganism, if I know the food, if I know the temperature, pH, all those things, mu max is known. For example, I am telling for E. coli, specific growth rate in nutrient broth at 35 degrees is 0.6. For example, I am telling per hour. You do this experiment in India, Tamil Nadu, in USA, wherever you do, if your culture is same, your media is same, and 35 degrees there, how much inoculum you are taking, nobody asks. I will not ask you how much glucose you took, nothing. Your maximum specific growth rate will be 0.6 only. So this is mu max is constant. It is like an identity card for a microorganism, media, and condition, temperature, pH. If these things you fix, then mu max is also fixed. So mu max is rather a parameter which we normally bother about. We should, in many study, you will find you are talking about maximum specific growth rate in bioprocess. So that thing we already discussed. And just one more line I will going to add. This is for mathematical purpose. For all bioprocess calculation you will be doing. I told you, okay, mu is 1 by x dx dt. I told you, right, very beginning. So from that, can I do something? If I integrate it, you know the integration, right? So for example, initial biomass is x0 and at that time x. For example, mu is constant. Mu is not permanently constant. Very small time period, if I am doing only for half an hour study, then mu is constant. So I can take out the mu, and this part is dt. 0 time 0 is 0 and time t. So what is happening here? Integration of dx by x. How many of you know that? Ln x, right? What is the limit? x0 to x mu t, limit 0 to t. So what will happen here? Ln x minus ln x0, yes or no? or simply I can say ln x by x0. If you know the logarithmic operation in mathematics, t minus 0 is simply t. So what I am getting, ln x by x0 equal to mu t. If I remove the logarithm, what will happen? Anybody can tell me? If I say x by x0, anybody of you know? Logarithm, exponential, all those things? Any one of you? It will be exponential of whatever is there. So x by x0 is exponential e to the power mu into t. E is exponential, right? Base 2. Now, so what is x? X equal to x0 e to the power mu t. So at any time, if I know the initial biomass concentration, if I know mu, I can find out what is the biomass at any time. And how the graph is made? If I make a plot of ln x by x0, for example, you are measuring the biomass concentration for growth. Okay, you are growing a culture, and every time and biomass you are measuring. Initially, you know how much biomass. After 1 hour, after not 1 hour, after 10 minutes, 20 minutes, 40 minutes, 60 minutes, you are measuring at different time. And then you can make, if I know x, I know x0, I'll divide it, then I make a logarithm, and I'm going to, for example, I'm making a plot. So I may get a straight line kind of things. So ln x by x0 versus time, if I make a plot, you see, ln x by x0, this is, for example, y. T is our x. So y equal to mx. So this is the slope. The slope will be mu. Are you clear about this? Are you getting this point clear?
Yes, sir.
Other people, other students, please. I am getting one equation,
Yes,
ln
sir.
x by x0 equal to mu t. So if I assume this is y-axis, you see, I'm plotting y-axis, and time is my x-axis. So this equation become y equal to something into x. Y equal to mx is a straight line. So if I make a plot, these points, if I try to join them, I'll get a straight line kind of things. And the slope of the line is mu. So you can also find out specific growth rate at any small time. Specific growth rate is not universally constant. Very small time period, what is the mu, I can calculate. So this is the way normally people do calculation of specific growth rate as we are talking about microbial growth pattern. So I just introduced all those things for this reason. How the growth phase, stationary phase, death phase, monod model, monod kinetics, I already talked about that. Okay. Now, when you are talking about fermentation, I'm coming into the chapter. When you are talking about fermentation process, I told food is very important. You already learned that, right? If substrate concentration is high, specific growth rate is high. If it is low, specific growth rate is low. All those concepts is clear. Now, what is required? If my microorganism where I am growing, if it is aerobic, I have to provide air. Okay. So we need to have oxygen requirement for a culture. Culture is growing, right? It is taking, like you are breathing, right? Every time when you are breathing, we need to give some, for example, 15 to 18 liter of oxygen per minute. You need to provide. Similarly, microorganisms also need oxygen who are aerobic. So oxygen supply in a reactor is also essential. So they have a minimal oxygen requirement. They need minimally this. If you reduce the oxygen, what will happen? Culture will die out. They cannot grow. So basically, when you are running a fermenter, we need to assure that we should have a column where we can provide oxygen. And what is the superficial velocity? Normally we will say superficial velocity is simple. I'll just talk about, they're telling superficial velocity of 0.1 meter per second. What is superficial velocity? I'll just draw a diagram, aeration. So please keep in the mind terminology when I'm talking about superficial. What is that? For example, I'm having a fermenter like this. Very big fermenter, round fermenter, for example. and bottom I am having some aeration device, bubbles are forming. Like in aquarium, fish tank, you are providing one oxygen line, okay? So how much liter of oxygen you are allowing per minute, you know, right? And what is the cross-sectional area of the surface? Because it is a circle, right? It is a cylindrical vessel, so it is a circle. This cross-section is a circle, right? So for example, I know the cross-sectional area is, for example, 2 meters square. For example, very high I am talking, 2 meters square, the surface of the liquid. And air bubble is coming, and you are allowing air bubble 5 meter cube per second. Okay, you are allowing the air bubble to come 5 meter cube per second. So what is the linear component I am getting? So this will come through this cross section, na? Okay, this will going to come in per cross section. So what is the linear velocity you are expecting? What is the linear velocity? Centimeter per second. I can find out. So if I know the flow rate, and if I divide by cross section, so superficial velocity is actually flow rate divided by cross section of your fermentation liquid. So for example, in this case, my sparger is passing 5 meter cube of air per second. And area is 2 meters square. So here meter cube, here meter square. What will happen? 1 will go. So it will become 5. So what is the things coming? 2.5 meter is still there. Second is also there. So superficial velocity is, for example, 2.5 meter per second. So if I am having a very big reactor and good aeration is there, so we can expect some 0.1 meter per second should be the superficial velocity. You see, the maximum superficial aeration velocity tend to be less than 0.1 meter per second. So we should not go so much high velocity. If you run so much high air, what will happen? Okay, I'm having very simple question. Everyone knows if I pass more air, it is always good, right? Yes or no?
Yes, sir.
Okay, fine. If we pass it so fast, it is good only. A large amount of air I am passing. But there is a problem. For mixing, air is in a gas bubble, right? It is a gas. You can see the bubbles, right? It is not dissolved. If I put some sugar in a water, can you see that after some time that this is sugar, this is water? Can you identify? No. This is a complete solution. But when some gas bubble is coming, so it is inside water? No, it will come out. If it is a bubble, if it is still in a gas phase, it will come out. There is no use. So for example, you are going for some dinner party or something like that, and who is serving is running so fast that you cannot pick up the food. That is no use. Very slow service is not good. Very fast service is also not desirable. You cannot take it up. So same thing happens if the bubbles need to have some time. Okay, the bubble is rising, right? You try to understand. So for example, I'm talking about just one bubble. I'm just talking about one bubble. So for example, this is a very big air bubble. This is inside, what is there? Air. So what will happen? Air from this bubble, air will go inside and dissolve, right? It is like a film, liquid film. To film theory, I will talk about mass transfer later on in our class later on. So what will happen? Air should get dissolved, and for dissolving it needs time. So very small amount of air from the bubble will actually come, and this is a very big resistance. It is a barrier, like an umbrella kind of thing, skin. Of course, this skin is not like your skin, but still it has a big resistance. So it has to, from gas phase, it has to come gas phase. Then outside there is a liquid layer, right? So it has to cross the liquid layer, the molecule, for example, oxygen molecule. Then it will only dissolve and it will come inside the water phase. That means then it is dissolved. Dissolved means you cannot see them, but bubble you can see. So what will happen? Bubble will actually slowly dissolve out. If you are running it so fast and only liquid layer is this, right? What will happen? Without dissolving, it will come out. Okay, without dissolving, the air will come out. That is actually wastage of your aeration. So you should not have very high airflow rate, and you should not have very low also. You are running a bubble that only you are allowing so slowly that the bubble is taking some 5-minute time. Then what will happen? In a minute, only one bubble will come up, right? That is not sufficient. Even if completely dissolve also, not sufficient. So you should have a optimal aeration rate in your feeding system. I hope you understood the logic, right? If I am running very fast, not good. Very slow, good for dissolving, but only I will get only 1 or 2 bubble per minute. It is not sufficient. Microorganism needs more. So that aspects you need to consider when I am having superficial velocity. I need to have oxygen requirement. Microorganism need some amount of oxygen, and you need to tell how much is required, how much is essential. Third thing I will talk about is about some space. You cannot fill the completely, because most of the time when I'm making a fermentation process, I'll always show that some of the liquid, above the liquid, some empty space should be there. If you complete, because this is for disengagement, air bubble will come out, oxygen will come out, you need to give some space. So they will come, accumulate, and they will come out. So you should not fill completely any bioreactor. If you have seen any operation in any bioreaction process, maximum 80% of the volume is filled, 20% is empty, and that is called, what is it called? Empty space is called, anyone know?
Vacuum.
Are you getting my point? 80% I am filling with liquid, but some space is there, empty. And what is it called normally?
Void.
Okay, very good. But there is some terminology also. It is called head space in fermentation terminology. Head space, empty space, because it is head. Why I am telling? Because it is above, right? So head space means top portion which is empty. Empty does not mean that it is vacuum, right? Not vacuum, because air bubble will come, carbon dioxide will come from microbial fermentation. Carbon dioxide bubble will also come out. So this space is gaseous space, and finally you will drain it out. The gas phase you will allow to pass out. So this portion, some around 20% of the volume, normally we keep it empty. Only 80% we normally fill the liquid. So for example, I am having 100-liter reactor. That means I cannot put 100-liter media. I should only put maximum 80-liter of media. 20-liter you keep. But by the way, these are only for, this is not any hard and fast rule, is not there. Just for guideline. You may say, sir, cannot I put 82-liter? Of course you can put. It is not like so stringency is there. It is a guideline. Most of the time in bioprocess, we will be only giving you guideline. There is no strict regulation whether you will do it or not. For example, I am not having much aeration is not required. It is very slow culture. I can put 90%, I can fill also. No problem, because I do not have any aeration. So liquid is not mixing so much, and you are having a agitator also, right? If it is completely filled, then agitation will not be good enough, because agitation will cause some liquid column, right? Vortex will be formed. So I need little bit more height also. Okay, so basically some empty space is required for deposition of air, and that air can be actually utilized for a space for disengagement of the air, and some empty space for easy operation. So these are the requirement. Now if I say what is the other requirement we can have when I am running a fermentation process is temperature control. Temperature control is very important. Any micro, I don't know, have you seen it or not? If I am growing any microbial culture, there will be heat will be generated, aerobic culture. Like in your system, you are also aerobic organism, right? You are not microorganism, you are a very big organism, but you are also aerobic. So fermentation process is not happening with you, but respiration is definitely happening. And when respiration is happening, so oxygen you are utilizing, you are burning out. Burning does not mean that you are just making a fire inside you, not like that. But essentially food ingredients are broken down and we are going to get ATP. I think you will study biochemistry, you will learn better on that. And so you are maintaining your body temperature. Some heat is definitely generated. How you are maintaining? Sorry, 37 degree. Of course, your body need to produce heat. That's why it is maintaining. When I'm growing some microbial culture also, if I constantly grow, they will also generate heat. And this heat is coming into the liquid broth. So its temperature will slowly rise. If you do not make it cool, so I should have some cooling system. Temperature control system should be there. I can put it in an incubator like we have in a lab. Okay. So this incubator is maintained, for example, I'm maintaining at 25 degree. If I switch off the incubator, culture temperature will slowly rise because of the metabolism. Cells are doing the metabolic reactions and heat is definitely going to generate, and those heats need to be removed. So I need some cooling, I need some refrigeration, I need some incubator which will maintain the temperature. And this is very important in case of fermentation also. When I'm having a fermenter, big fermenter, so we can have some cooling water system. So for example, this is one jacket. Okay. So there will be two entries will be there at the bottom. Water will come inside. This is inside glass, and this is empty space. Okay, it is locked, for example. So water will come and it will go fill up whole the surrounding, and finally it will come out. So you are allowing cool water, chilled water, and this is your culture broth, right? So for example, this is culture broth. So what will happen? Across the glass boundary, heat transfer will take place. So your culture will become little cool, and the cool water will become hot. So heat exchange is required. In most of the process, heat exchange in a submerged liquid phase fermentation is called submerged, right? Submerged means inside water. Okay. Submerged fermentation process, I need to have some cooling system. Sometimes I also need heating system also. When if I am doing the study in a country where temperature is 10 degree or maybe minus 20 degree outside temperature, room temperature. So that case, it will be very difficult. My media will also become minus 20. So then that time I have to provide hot water. Okay, so that culture will be a little bit hot up and it will go some atmospheric, I mean to say optimal temperature can be maintained. So heating and cooling both may be required depending on what kind of culture you are growing. You see? So heat generation is there. So heating and cooling of large fermentation take time and it should be done with care. Now I'll show you some example of bioreactor design. There are many kinds of bioreactor. You can study this paper. I'm just overview I'm giving. The best widely used fermenter is starred tank. I'll show you the diagram rather. I think you can see the diagram very easily, right? You can see my screen. Can you see the screen? Yes, right?
Yes,
Okay.
Yes, sir.
Okay. You see, there are different kinds of bioreactor is used, but when we are talking about fermentation process, the most widely used is this one. This one is most widely used, and this kind of reactor when we are running is more easy to operate. They have a impeller, they have baffle, air inlet, and we are having a agitator, right? This blade is rotating. This is the axis of rotation, rotating. So this is one kind of reactor, and you see, so first one is stirred tank. That means we are having a stirring device. You see, we are stirring. This case B is an example of bubble column. Just a second, please. Naresh. Hey, good morning, Naresh. I'll call you after 20 minutes, Naresh. हाँ, क्योंकि मेरा एक क्लास चल रहा है, ठीक है? नहीं, हम 10 बजे करते हैं तुम्हें. हाँ, 5 मिनट के लिए. हाँ, ठीक है. So second reactor you see is a bubble column. So here the mixing is done by the stirring device, right? I'm having, for example, an impeller, axial rod, impeller is there, it is mixing. So in this case, you see nothing is there. Then what is happening? The bubbles are forced. So if some bubble is coming up through a column, it will also cause mixing, right, of the liquid. If bubble is constantly coming from the bottom to top, of course, little bit higher velocity. It should not be low velocity. So this kind of reactor design is also used. Then you would say, sir, why we are not using this one? We are using this one. Can you tell me what could be the reason? Here only air bubble is causing the mixing. Mixing is required, right? When you are making even some liquid fermentation process, we need to mix. Otherwise, cell will settle down. Continuously, I have to mix. How I will achieve mixing here? I am not using any baffle. I am only using air bubble to mix up. Okay. So this is actually bubble is rising on the column. That's called bubble column. Okay. And can you guess why we are using this kind of things? Any guess? Guess is fine. Any one of you?
Cost reduction, sir.
For what?
Cost reduction.
No, I'm asking why we should adapt this. What is the reason behind that? Any benefit here? Can you see? Any benefit? Yes. There is two benefit I will tell you very easily. In the first case, I am having a rotating disc, right? It is rotating at high speed, some 400, 500 revolution per minute. And liquid is all swirling. There is many cells. Bacterial cells are okay. They can take little bit of shear force because their surface will be rubbed. Na? If I put you in a washing machine, what will happen? You will be always rotated. It is too stressful for you. Similarly, for bacteria also, if it is rotating disc is there, they're always impacting the bacteria. Of course, there is very small, but there will be cell damage in the rotating disc. So if the cell is very sensitive, they cannot bear the shear force, then I should not take this kind of stirring reactor. I can have this one because air bubble is little bit smooth, right? Of course, air bubble is not going to hurt you so much. So if the cells are very sensitive to shear, I should choose this one. This is the first reason. Second reason, running this impeller and mixing device, we need large amount of energy, constantly rotating. You see, it is too costly. Here, no such cost. I am putting the air in a compressor and slowly releasing. So 2 hour, 3 hour continuously bubble is coming. What does it mean? I can save the energy. So first advantage of here is for cell, you can think, right? So it will save energy. One reason. Second is it is good for cell who are or which cells are little bit a problem for having the so much shear force. But here also mixing is not really complete here. We can have another. Okay. So for example, here we are talking about bubble column, but bubble column can also have some variations here using this. You see this device here upcoming and going. So riser means bubble will rise and the liquid will come down again rise, come down again. So here two different. Riser means where bubble is rising. Downcomer means liquid will come, bubble will not come, bubble will go away. Here you see, here we are putting the air inside in a baffling system. So here this baffle means the plate rods. So liquid will go, bubble will go, and some will come down, and again it will go. So basically up and down, this circulation is happening. In this case, it is just one directional, right? Singly go and come. But here, little bit recirculation. Recirculation means mixing will be good. So these kinds of reactor is known as air lift. Internal loop air lift, external loop air lift. So air lift means air is lifting the liquid and recirculation is happening. So this is all about air bubble. The last one I am showing here importantly is no air bubble. Air is there, but air bubble is not the cause. Here we are having the biomass itself is rotating. Biomass is not very small. They make some big flocks. Okay. Fluidized biomass. So we are not using single cell, right? Maybe we are giving some support. So bacteria will adhere on the small support. So they will look like a ball, not big ball, small ball definitely. And when I'm putting the aeration, so they can fluidize the biomass. So biomass is actually rising up. Of course, we can take out the liquid. Again, we can feed it back. So you see, this case of reaction is also possible. That is called fluidized bed. Bed means where they are sitting. So here biomass itself is rotating. That is called fluidized bed. So basically, these 5 important reactions normally we take for the fermentation process. The design. Last one is packed bed. You see, the bed is completely packed. So here microorganism and some packing material like sand filter you normally see, na? So on this microorganism is already attached, and you are putting the nutrient, coming down the nutrient, gas will come out. Very simple design. Energy consumption is there for air, because here pressure is much required, because there is a big packing, right? Big packing means pressure is very high. So you need to have high pressure air to go through this. So air will come from the down and go up, right? But there are so much of packing material, so it will be a little bit problematic. So energy requirement for aeration is there, but otherwise a simple design. Nothing is moving here. So these are the type of different kinds of submerged bioreactor system people normally adapt in fermentation process. The next part I'll talk you in our next class. This is the different kinds of reactor. Please keep in mind, most widely used this one, fermentation. This one is also most widely used for fermentation process in many cases, but mostly anaerobic. Air is not so high requirement. And this is also used for wastewater treatment, not for some bioproduct formation. So we can see fluidized bed. Fluidized bed. Bed means biomass is fluidized. Fluidized means flowing through. It is coming up. Fluidization process, right? So this is fluidized bed. This is packed bed, and this is continuous stirring reactor. These are very widely used. These reactors are actually useful. This one, and this one. Where in the 3 cases air bubble is there. You see, air bubble, air bubble, air bubble. And the 3 cases reactor is known. One is bubble column. Just go. Other 2 are known as airlift. Name is just different. That's all. So these are the different formation of bioreactors. We will be talking about different kinds of bioreactor configuration, not operation. Configuration, structure. That is very important for us to understand. And okay, that's where we will close the discussion today. Next class possibly we will talk about the design of the reactor in more detail from your textbook. Okay, I think our time is over. I have to stop it now. Any questions from your side? I find you people are very silent. Any questions from your side, please? Any queries?
No, sir.
Bisruth, can you see me?
No, sir. I can't see you, sir. It's a colorful rainbow type image.
I understand. Then there may be some, I don't know, this Google Meet knew some option schemes and we cannot really adjust it. I'll check out next day. Now I'm seeing only I'm not visible. Anyway, we will let you know. Okay. If there is no questions, now I think it is working again.
Yes, sir. Now I have
Yeah. So if you have no questions, then you can leave. If you have any queries, you can just ask me.
Thank you, sir.